Dimensional Analysis, Part 2, Wiens Law. Dimensional analysis is a complicated-sounding term for a straightforward idea. It just means keeping track of your units and performing unit conversions wherever you find you need them. In this video, we will use Wiens Law as an example of an equation where you might need to perform unit conversions to make sure the units work out. Wiens Law states that the peak wavelength emitted by a radiating black body, here represented by lambda max, is inversely proportional to the temperature of that object, T in this equation. Here the constant of proportionality is the letter B. Rewriting this equation to include the units in each term, we have that lambda max, the peak wavelength, is in centimeters, T is temperature in kelvins, and the constant B is equal to 0.29 centimeter kelvins. Now let's show the example needing unit conversions. Let's say you discover a star that is radiating most strongly at the infrared wavelength of 950 nanometers, and you want to use Wiens Law to determine the temperature of this star. If you solve the Wiens Law equation for T, you have T equals 0.29 over lambda max. But in this case, the peak wavelength is given in nanometers instead of centimeters, so we must convert. Since a nanometer is 10 to the minus 9 meters, 950 nanometers is equal to 950 times 10 to the minus 9 meters, or by shifting the decimal, 9.5 times 10 to the minus 7 meters. By looking at the units in the Wiens Law equation, you see that you need to convert meters to centimeters in order to cancel with the centimeters and the constant. The conversion factor 100 centimeters per 1 meter can be used to rewrite the wavelength as 9.5 times 10 to the minus 5 centimeters. Note that when you write the wavelength in centimeters instead of meters, the units cancel, and you get a temperature of 3000 Kelvin for this relatively cool star. By converting to the correct units before even plugging into the equation, you are demonstrating that you understand the concept of dimensional analysis.